Sure. What's the plate? 29 number? 29 THD03. 29 THD03. T HD03. HD03. D 03. 0. 3. Hey Flash, want to hear a joke?
You know, like one of my habits every morning is that I would go to Starbucks to buy some stuff. And one thing that really bothers me is sometimes people like to have small talks with the attendee, right? And sometimes, like, there was a long line behind the person who is currently talking with the attendee, and my feeling is like, come on, no more, right? So today we are going to talk about something that we can reduce the wait time of instructions. But before we start, let's remind us where we are coming from. So the last lecture we talked about to deal with data hazard in your undergrad study, we have learned data forwarding. And I bet a lot of you might spend a lot of time in researching on those pipeline diagrams in your undergrad textbook, and you probably have that kind of question like testing this, testing that for data hazard detection, and where can I do data forwarding. However, one thing that we have learned the last time is that, well, for data hazard, like modern processors, like the one that we have been doing assignments on, we have like a 5-cycle delay, even though you have perfect cache, right? So what does that mean is that as long as you have a data hazard that depends on the memory access instruction, which is typically the case why we have data hazard that we have to wait. The 5-cycle hazard is like, even with that 5-cycle delay, even though you have the data forwarding, it only helps you by 1 cycle, which is not really significant. And so, it makes sense in the past when the memory processor performance gap wasn't that significant. However, this is not true, right? So I always wonder, like, why do we spend so much time in teaching students this kind of technique, this kind of mechanism that works for 30 years ago, but not anymore? So today we are going to talk about something different to deal with the data hazard. But before we talk about how to deal with data hazard, can you remind yourself where in your life you think some place that is always inefficient, and why is that inefficient? And if you can elaborate more, like, how do you make it more efficient? Grab a few people around you and talk about it. All right, like where in your life you think it's more very efficient all the time? Don't be misled by the picture I put here. I'm just saying that. Well, the video we played was from Zootopia. I heard Zootopia is having a second version pretty soon. Hopefully, that will be a great movie. But like, where in your life do you think is always inefficient, and why is it inefficient? Lines at Disney, okay, but why? Okay, a few. So you are basically saying that there's limited amount of availability, and there are too many people around. Okay, so that's not really solvable unless you have many like roller coasters of something, right? What else?
Meetings at like work with a bunch of people who don't need to be there.
Hmm.
Just like talk about stuff that's not important.
Okay, talking about stuff that is not important. Okay, that's one thing. That's one thing I found oftentimes that happens in companies. So, like one thing that I found, you know, you might think about like professors with like meetings, but I'm that kind of person that I hate meetings. Like like most of the time, I hope that I can only meet my student like only like 15 minutes for the regular updates, and then we only talk if we need more detailed discussion on technical stuff, like if I really need to teach them something. And it's a cultural shock when I work at Google a few years ago, is that I found my schedule is like filled my meetings. So a lot of cases, so that's why people have to work really late. Like my team, a lot of us, we work until like 8 p.m. or 9 p.m. every day. And the main reason is that if you look at our schedule, like between 10 to 4 p.m., it's always meetings. And I am so surprised that why am I having so many meetings every day? And there are meetings with my manager, there are meetings with other collaborating team, try to convince them using our stuff. And at the end, like the first 3 weeks, every day I have a lot of meetings. So I talk to my like my collaborator, and I said, well, like, yeah, I know we are in a phase that we have to discuss with our collaborating team regarding where is the position of the framework we are going to implement. But I think somebody has to get the things done so that you have more numbers to convince them. So I convinced him that I shouldn't have so many meetings. And at the end, after I end my visiting, like some of my manager were asking me, like, like, do you have any suggestion for our team? And I put one thing. I said, too many meetings. Like 3 months later, when I visit the same team again, and and I was asking him, how do you feel like your life right now? And like my some of my friends who are still working in the team, uh, they say, well, surprisingly, we don't have that many meetings as before. And I say, woohoo, they really listen to me. All right. But meeting, I agree, is something that's really inefficient if you have too many people involved. What else? I know you have this in your heart, right? Like anyone think like DMV is inefficient. Why is it so inefficient? Mm-hmm. Okay, so everyone has to go to DMV, right? And you have multiple workers, right? But why is it still very inefficient? If you have a lot of people, like each DMV, we have a lot of people in there, right? But why is it very inefficient? What? Scheduling? Okay, talk more about it. Uh-huh. They do what they need to do and get out, right? And so here are the a lot of things that I feel about DMV. Like, the first cultural shock when I arrived in the United States is that when I go to the DMV, So I heard DMV is very inefficient. So on the day that I take the driver's driver's license test, like the paper test, a lot of people saying that you have to read the questions before you get there. And because I was super busy at that time, so I didn't even read the question the day before. I was like taking a bus, and the bus is around like a 30-minute ride from my place to the DMV in San Diego. And then on the bus, I started reading the book. I haven't finished reading the whole thing, but when I arrived there, I waited for another 2 hours, which allowed me to finish reading the whole book and turn on my personal device to see more questions, like sample question, go through all of them, and I still have time. And then finally, I took the exam. So that was my first cultural shock, and it's pretty much exactly what like they happened in a movie, that you arrive there super early. Like I think I went there after I finished my breakfast, and then when I get out, it's the time for lunch, right? So they were trying to improve DMV in 2020. They have McKinsey. I don't know if you know that company, but it's probably one of the most famous consulting company. And surprisingly, it's still not as efficient as you want. So this example still works. But today we are going to talk about how can we make the processor more efficient. But before we start, right? So let me extend the variable swapping example a little bit more, because most of the time you should imagine that like this kind of code example, we ran it in the setup of a loop, right? So right now with data forwarding, the best we know that every time when we have the dependency between this two, we still, when we have the dependency between instruction 2 and 3, we still have to deal with the 4-cycle latency, 4-cycle stalls because of the data dependency, right? So that's the main issue that we are dealing with, right? So it's pretty much coming from this data dependency, right? So now I'm asking you this question. So if today I can be a little bit more, if you are the compiler, can you do anything to make the latency shorter? All right, let's take a look. Okay, so it's probably something that we can sync up with others and see if we are going to see a different answer of it. All right, let's take a look. So after discussion, more of you think the answer is A. There are still some of you think the answer is C. So first of all, if I try to reorder 3 and 5, would that help us to reduce stalls but still make the code correct? Can we reorder 3 and 5? Can we reorder 3 and 5? Because some of you pick C, right? Can we reorder 3 and 5? Can we reorder 3 and 5? Can we reorder 3 and 5? No. Why not? What's wrong with 3 and 5?
If we add 8 to RAX first and we override it with the value of R8, then that add will be lost.
Right, so here's the thing, right? So here, the RAX is the base address that should be identical to the previous two so that we can move the value to the right place. However, if you try to move this one here, then the RAX value is going to be advanced to the next element, which is not something we want, right? So very importantly, remember, if you are the compiler, you want to modify the code, the only thing that you cannot violate is the correctness of the code, right? So you cannot do this. So how about 1 and 2? Are we having trouble with that? So why don't we have trouble with 1 and 2? Why do we not having trouble of reordering 1 and 2? Why is it okay to reorder 1 and 2? It doesn't affect the correctness, but what's a fundamental reason why it doesn't affect the correctness? What? They are not depending on each other, right? So based on that, right? So if you pay attention to this, right? Let's see. If I reorder 2 and 3, would that affect the correctness? 2 and 3, would that affect the correctness? Yes, right? So we cannot reorder 2 and 3. How about, so 3 and 5 is also affecting the correctness, right? How about 4 and 6? It also affects the correctness, right? So 1 and 2 can be reordered, but would do this affecting, like reducing the cycle stall? Because Okay, so the reason why we have 4 cycle stalls is because we have 2 and 3 as a data dependency, right? So if you move 2 earlier, you are actually moving down 1 to fill in that data dependency, right? So that's how we can reduce the stall, right? So the only one that could be reordered is actually 1 and 2. However, some of you were thinking about 3 and 5, right? So the truth is that if you could have reordered 3 and 5, like by smartly rewriting your index in this way, right, you are actually able to do that. Right? Did you see that? Right? So if you could have done that, right, then here's the best you can do, right? So if you could have both reordering 1 and 2 and also reorder 3 and 5 by rewriting these pieces of code, right? Then you can eliminate the 4 cycle stalls to be just 2 cycles, right? Are you satisfied with that? Yes? Okay. So with that reordering, right, we still need 9 cycles for this 7 instructions on average. So you can imagine the CPI of running these pieces of code is going to be 1.29. Are you satisfied with this? If you are the DMV, right, like you are there, right? There is always like two slots that are always wasted, right? Do you like it? Okay, let's do something that's more creative, right? So now, I mentioned this is a loop, right? So what if I know ahead of time there is going to be a lot of loop iterations that I'm going to run. Like if you are the DMV, you know, like every day we are busy. I always have people that I can run, right? Then what I can do is more aggressively, right? So previously we are pretty much do things loop iteration by iteration. But if I know there are many iterations going to be there, I know for sure the upcoming iteration is going to be there. The opportunity here is that what if I grab instructions from the next iteration to run, to fill in the slots, like for example, like this two, can I make them run earlier, right? So if I do this, what happens is if you schedule it carefully, except for the very early iteration, you'll figure out that later on, you are always able to output 1 instruction a cycle, right? So what does that mean is that you are having a CPI equal to 1. If you can do more aggressive interloop optimization. But the question is that, can compiler do this? Can compiler do this optimization? Can compiler optimize your code in this way? Why not? You cannot know if it's going to run that many times, right? But is there any architectural component can predict the future if we are going to run this iteration or not? What is that? Branch prediction, right? So with branch prediction, it is possible for the processor to predict if we are going to run this iteration or not, right? So then if processor knows how to run that, right, then why we really should have a hardware solution taking advantage of the fact that we have the opportunity of inter-iteration optimization and out-of-order execution, right? So what we are going to talk about today is actually this topic, using processor prediction to unroll the loop dynamically for exploiting the opportunity of out-of-order execution. So today that's actually the main topic, and it's probably the most important topic in CS203 in terms of microprocessor design. So the content of the lecture today is going to be an important piece in your final exam, as well as the comprehensive exam question is going to be today's lecture. All right, so we are going to talk about out-of-order execution. So first of all, thinking about when are we being able to execute an instruction? What are the criteria that we are ready to execute an instruction? First of all, the instruction must be presented in the instruction queue already, right? It's already fetched. And the second thing is that you can execute the instruction if data dependency are resolved, right? And as long as, and the third thing is that the target unit is available, right? So, you know, there are often times when you sit in a DMV, you see someone is apparently idling after the counter, after a window. You see that all the time, right? They are sitting there, they are not doing anything, right? But I fill in the questionnaire they want me to fill. I have all my documents, all my IDs ready. I just need to renew something, right? They don't call me. Why is that? Because they want to do things in order, right? They always say like, A, now serving A16 to window number 34, right? Something like that. And it's never like A17 and A16. Why is that? Because they want to do things in order. And sometimes, surprisingly, like saying like you are A17, right? And the A16, surprisingly, have a data dependency issue that people have to call Sacramento, right? Like, you know, I do have the experience that I always feel like sorry for people behind us. So I was taking a friend of mine to the DMV for the behind the wheel test. And my friend is an international student, so apparently there are always issues with them for the international students documentation for like if they can legally stay here for this amount of time, that kind of stuff, like their I-20 or I-94 is not up to date. So it turns out that they have to call Sacramento. And you thought they were going to, they will have a hotline, but turns out no. When they call Sacramento, there is always like some kind of automatic system for them. And then there might be music playing, right? And then probably like tens of minutes later, someone in Sacramento catch up the phone and address their issues. But the problem here is that, you know, when the staff who is trying to help us, waiting for the phone call, the staff is actually available for other things. But because they have to serve us in order, they cannot call others at the same time, right? So that was the problem with the inefficiency of DMV. But here is the thing, right? Thinking about executing an instruction, once you have these three criteria being satisfied, why can't I put my instruction into execution? Why do I have to stick it with the compilation order, right? So that's a philosophy of dynamic scheduling, is that the best way of scheduling instructions should be just based on the data dependencies you have, right? Like previously, when we talk about if we should reorder these instructions or not, simply based on if they have data dependencies, right? Do you remember that? Like, I think Nick just said it, right? Like, because they don't have data dependency, right? So the very basic concept to find out the opportunity of dynamic instruction scheduling is to look into the data dependency, right? So the data dependency, so that's why in the beginning of this section, we were talking about identifying data dependency. So today, when we talk about data dependency, we have to have some better method of analyzing it. So the way I'm introducing today is that we first need to draw a data dependency graph. And for the data dependency graph, like for this first instruction, because it's the first instruction, so it's not depending on anyone. So now looking into the second instruction, is it depending on 1? No, right? So 2 could be a separate node. Now, regarding instruction 3, is it depending on anyone? Who? 2, right? So if there is a data dependency, let's draw an arrow like this, meaning that instruction 3 needs the input from instruction 2. Now, looking at instruction 4, is it depending on anyone? It is depending on 1, right? So you can draw an arrow like this. But here, through this simple representation, you can know it doesn't matter 1 and 2 who go first, right? It matters only if 4 is after 1, 3 is after 2, right? As long as you didn't violate this policy, you can reorder. So let's keep going on. So for instruction 5, what is it depending on? Is it depending on anyone so far? Instruction 5. Is it depending on anyone? Is there a data dependency there? What's the definition of data dependency? What's the definition of data dependency? Right. So under that definition, are we allowed to are we having a data dependency between 5 and others? Are you sure? Are we waiting for 3 and 4 to give us any outcome? Right. So there is no data dependency for 5. Right. So there is no data dependency for 5. Right. But you might wonder, wait. Previously we said we cannot reorder them, right? So we will talk about that later. But here you should see this. In theory, 5 has no data dependency with previous ones. Now, looking at instruction 6, is it depending on someone? Who is that? Instruction 5. How about instruction 7? Who is it depending on? 6, right? Now, instruction 8. Who is it depending on? Who is instruction 8 depending on? What are the inputs of instruction 8? 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 I feel like I'm an NPC today. RDI and RAX. Anyone is modifying RDX, RAX. Who is that? Who is that instruction modifying RAX? Who is the instruction modifying RDUI? Okay, so only instruction 5 is modifying RAX, right? RDI remains the same, right? So what does that mean, right? 8 is depending on 5. Okay. Please pay attention to this lecture. I already tell you, this is going to be in your comprehensive exam. A lot of people in a review saying that they want more example. Right now, I'm running through an example. If you stay quiet, if you're not involved, I feel like I'm an NPC. Why am I doing this? Right? I am trying my best to help you. Try to help me. All right? Help yourself. How about instruction 9? Who is it depending on? Is it only depending on 5? Its input is what registers? RCX and RAX, right? So only RAX is modified. So only depending on 5, right? So how about instruction 10? Who is it depending on? What? 9. How about instruction 11? 8. How about instruction 12? Is it depending on 9? Who is it depending on? 5. How about instruction 13? 12. How about 14? Right. So one thing that you will learn, right, is, okay, so these two, they are independent chains, right? And for this, like this pile, as long as you address the 5, the other, they are also independent data dependency chains that you can schedule freely, right? However, previously, we are hitting into the issue where we have trouble reordering 3 and 5, even though they don't have data dependency, right? And in fact, the reason why we cannot reorder those is because we have the so-called false dependencies. The false dependency means that those are not true data dependency, because I said the definition of data dependency is only because a later instruction is depending on the value of an earlier instruction. But for instruction like 3 and 5, it's actually simply because instruction 3 is using a register, instruction 3 is using a register that instruction 5 will modify. Right? And this situation is called write after read, meaning that a later instruction overwrites the source register of an earlier one. And similar to this one, there is another situation which forces us to not being able to reorder the instruction. It's called write after write, meaning that a later instruction is overwriting the output of an early one, right? So like instruction 9 and instruction 8, they cannot go before instruction 1 and 2 because you are going to destroy the value in RSI or R8, which instruction 3 and 4 may later on need to use, right? So because of those, we cannot really reorder instruction as what we want. It's because we have false dependencies to limit the freedom of reordering. So if you pay attention carefully to the situation of the false dependencies, it's simply because a later instruction overwrites a register. It's just because I overwrite a register. So to deal with that situation, what can we do? What should we be doing? So here's the thing, right? Since the main reason why we will overwrite the current value in a register is simply because we need to reclaim the original register for another instruction to use as its output. If we can do this, the best thing to do is to just give every output a new register. Then I don't have to worry about not being able to reorder these instructions, right? So let's try this, right? So if I can give each instruction with an output with a new register, like the code on the right-hand side that I have been rewritten, right? So for example, like instead of moving to RSI now, it's going to be T0, and R8 is going to be T1. Then the later instruction, I can modify the source to be the newly named register. And for this 5, instead of having it to RAX now, it's going to T2. And the later instruction, depending on the new RAX, will be depending on T2. Then, are we seeing any problem when we reorder 3 and 5? Not at all, right? So you can find here the key of supporting dynamic instruction scheduling through simply based on the data dependency is to give the processor more registers that can allow themselves temporarily storing their output, right? So this mechanism is called register renaming and speculative execution. So this mechanism is described in the assigned paper, MIPS R10K Superscalar Microprocessor. And I know you might spend a lot of time reading your textbook regarding Tomasulo algorithm, scoreboarding algorithm. I don't think any real processor is implementing that. So I completely skip that. If you take other professors, that's what they are going to teach you. But I'm not going to teach you that. But one thing that I want to mention is that you have better to pass the comprehensive exam this time. Because I'm 100% for sure if they are testing you the comprehensive exam of another 203, those are what they are going to test. So this is really important, right? Register renaming plus auto-order scheduling. So here's the concept of register renaming. As you can hear, register renaming. So the core concept is that for each of the instruction instance, I redirect their output to a physical register. So here we are introducing a new abstraction called architectural registers and physical register. So now you have here, sometimes architectural registers are also called virtual registers. So now you have a lot of like virtual and physical abstraction, right? So here is the thing. Here's the main difference here, right? So like when we talk about memory, there are smaller virtual memory space than then you have a larger virtual memory space. But it's totally different when we talk about registers. So physical registers, they are the real registers that your processor would internally use to run your instructions. And as we mentioned before, the main purpose of having physical registers is because we want to allocate each output of different registers. So you would definitely have more physical registers than your architectural registers. So for example, modern processors like Intel processors, you have 60 to hundreds physical registers. But on the programmer side, you can only use 16 general purpose registers that the instruction set architecture provides. So what does that mean is that the compiler can only use 16, the programmer can use 16, but internally, processor has 64 to 128 that they can use. So what happened here is that there will be a mapping table, which is pretty much like the virtual memory abstraction, right? Whenever you have an architectural register coming in, it will dynamically allocate a physical register if the instruction is leading to a new output of that architectural register. And the mapping table would tell you where can you find the up-to-date value associated with that architectural register. And they're associated with that mapping table. You want to know how many instructions are referencing that physical register so that you know whenever it's okay to reclaim that physical register for other instructions, right? So those are the two components, main components in the register mapping table. So whenever I have this, then on the hardware side, we will create an issue logic to check if all the data dependencies are satisfied. As long as the data dependencies are satisfied, I can schedule an instruction into execution. So now you can imagine in the modified pipeline, you are going to have a register renaming unit. You are going to have issue logic, right? However, it's not super safe to just execute instructions out of orderly because we have exceptions occurring anytime. So for example, whenever you have a page fault, to deal with that page fault, so first of all, the page fault can occur when you have instruction fetch or memory access, right? So what happened is that even though it seems like I'm just fetching an instruction, but if you meet a page fault when you fetch that instruction, your processor will jump to the operating system page fault handler to handle that page fault first and jump back to your original code if the operating system at the end decided to continue executing that process. So in this way, you can think about, even I don't have branch instruction, I might unexpectedly have to change my program counter direction because of those exceptions. And exceptions occurs all the way in a pipeline. For example, even when you are just doing LOU operations, you might meet divided by 0 or not a number, this kind of exception, right? So everywhere we might have the issue that we will branch out. So that's why your hardware may still have to make sure that I know what's the right order of executing instructions by committing the instruction. And I can only know if this instruction is safe to present it the result to the rest of the world until it reaches the very end of all the pipeline stages, right? So we can execute the instruction out of order, but when we finish or commit, it has to be in order. Otherwise, we cannot 100% for sure if every instruction have passed through all the pipeline stages, right? So turns out, when your instruction hasn't reached the end, it's in a so-called speculative execution stage, meaning that if the instructions still have the chance of branching out, if instructions still have the chance of not being executed at all, right? So this is the concept of speculation. So to deal with a speculation, we need two additional things. One is a hardware structure called reorder buffer, which keep the order of the instructions. And there is not really a specific way that how we should implement the reorder buffer. So the most common way of doing this is that we extend the instruction queue when we fetch the instruction. And then when we finish the instruction, we add a stage called commit and retire that check if this instruction has passed everything it needs to pass to be considered as finished. So you can imagine now at the end, I also have one more stage called commit. So this is the original diagram, but after the described logic. This is the modified pipeline. We would have a renaming logic, we have an issue logic, and at the end, we also need to use the reorder buffer to make sure that this instruction is ready to be commit. So this is the complete processor. So now, saying that I still have the same amount of functional units as the previous pipeline. And I'm still only allowed to put one instruction into execution through my issue logic every cycle. With register renaming, how am I going to execute these pieces of a code? So first of all, right, we still draw the pipeline, and now we have one more stage called renaming at the very beginning, and one more stage called reorder buffer at the very end. And for the issue, as I mentioned, any cycle, I can only put one instruction to execution. And so for the processor we have, the execution has the execution units that we can put into is either address generation, the very first stage of the memory pipeline, the LOU, the very first stage of an LOU instruction, the MUL, and the branch. Right? So only one instruction could be in either 4 of the stage at any cycle. So that's the restriction. Other than that, we are free. Now, for the first instruction, which is currently at the renaming, are we ready to execute this instruction at the next cycle? Are we ready to put this instruction to be issued in the next cycle? Okay, so if that's the case, which functional units are we going to? Which functional unit are we going into? Which functional unit are we going into? Which functional unit are we going into? Address generation, right? So in the next cycle, you can imagine every instruction is advanced one stage with instruction 1 at the address generation. Now, at the next cycle, since there's no data dependency, I can move instruction 1 out from address generation. So in that perspective, which instruction can I put into execution? Can I put instruction 2 from renaming to execution? Can I put instruction 2 from renaming to execution? And which target functional units? Address generation, right? Now, and in the meantime, for the register renaming, we can put a table like this, right? They are using this. Now, for instruction 3, are we allowed to put into execution the cycle after it's renamed? It's depending on P1 after renaming, right? Are we allowed to put that into execution? No, because of what? Because the R8 is not ready yet. Or sorry, the P1 is not ready yet, right? So at the next cycle, I can continuously advance these 2 instructions, but not instruction 3. However, I can try to rename one more instruction, put that in the queue, right? So now after I rename instruction 4, am I okay to put instruction 4 into execution at the next cycle? No, because P2, right? So now you can imagine in the next cycle, I'm advancing the other instructions, but also getting one more instruction being renamed. And that instruction is instruction 5. So for instruction 5, can we issue that instruction at the next cycle? Yes, right? So which functional unit are we going to use? Which instruction? Which functional unit? LU, right? So we can put this into execution in LU stage. And in the meantime, I can also rename instruction 6. So now looking at the next cycle, I now have instruction 3, 4, 6. Which one can I issue in the next cycle? Which one can I issue in the next cycle? Which one can I issue in the next cycle? First of all, can I do 3? Because for 3, it's depending on P1. Sorry, I think I got it wrong. So for 3, it's depending on P2 instead of P1. Right? So this should be P2, this should be P1, right? So, but how about instruction 4? Can I put instruction 4 into execution? Next cycle? Instruction 4 is depending on P1. At the next cycle, am I able to have P1 being ready? No, why not? Right? So because instruction 1 is right now in M4, right? After M4, the value is available, right? So why not, right? So how about instruction 6? Is it ready to be executed? What is it depending on? Instruction 5, right? So will instruction 5 ready its result in the next cycle? How long is the LU? So in the next cycle, will that be ready? Okay, so 4 and 6, they were both being ready to be executed. Who should go first? 4, because it's coming earlier, right? So first of all here, like in this pipeline diagram, we see that 5 is earlier than 3. So it's reordered, right? And now we are going to do 4 first, right? So this is another reorder. So 4 is now before 3, right? And be careful, this is like an optimization that the compiler cannot do for you, right? But the processor will do for you, right? And now after that, right, at this moment, when I get 1 ready, my logic can also check if there is any instruction before 1 having trouble. No, right? So I can retire instruction 1 safely, right? But in the meantime, I also have 5 that is in a reorder buffer that is waiting to be retired. But based on the logic we said, until all the instructions before me, I cannot retire, right? So now the next cycle, as you can imagine, we are going to be able to execute instruction 3, right? And then get 2 in a queue. But in the meantime, instruction Q, as we know, it should be retired after that, right? And then finally, once we have instruction 3 and 4 being scheduled, we can do instruction 6, right? And if you keep going, right, you can figure out that at the end, if you pay attention to this part, and if you count the number, you will figure out on average, every 7 cycles, we will retire 7 instructions. And every cycle, we are issuing 1 instruction. So what does it mean is that we are going to have a CPI equal to 1, even without any aggressive compiler optimization. That's the power of dynamic execution. So the approach that I told you is not the approach that I want you to answer your final. That's what other professor would typically teach you for a register renaming. So I'm teaching you an easier way for that. So now, if we are considering a case where we have sufficient amount of physical registers, so you are never going to be starved by the physical register you have, then the only thing you need to worry about is what? Data dependencies and the availability of your functional units, right? So this is how we are going to schedule. First of all, the horizontal, each of the column represent the functional units. And remember, since we have a pipeline, if we have a perfect branch prediction, we are supposed to be able to fetch instructions smoothly without being interrupted, right? If we assume our branch predictor is perfect, right? So every cycle we can have a certain amount of instructions coming in. So they will be queued cycle by cycle. And they will be decoded cycle by cycle and renamed cycle by cycle. So this front end part, we never have to worry about it. So what you really have to worry about is that, can we issue those instructions cycle by cycle, right? So what happened here is that every cycle, I'm assuming that I have an instruction that's ready in the queue. So for example, right now I have an instruction 1, so I put this node in the instruction queue. So given this instruction has no data dependency, am I ready to execute this instruction in the next cycle? And which pipeline am I going to put it to? The memory pipeline, right? So let's put it here. But in the meantime, in the same cycle, I'm going to have instruction 2 into execution, right? So for this instruction queue, and here, for each of the pipeline, it only represents the first cycle of its pipeline, right? So once the instruction is being executed, you can imagine that is already free, right? So if that's the case, am I ready to put 2 into the memory pipeline in the next cycle? Yes, right? So this is okay. Now I'm going to have 3. For instruction 3, are we able to put it into memory pipeline in the next cycle? Okay. Why? Data dependency with who? Okay, so based on the processor that we have been using so far, 5-cycle latency, when is the earliest possible time you are going to have 3 being executed? 5 cycles later, right? So we do this. Put an arrow, put instruction 3, 5 cycles later. So this is the earliest possible time we can put 3 into execution. At that time, it's already the earliest instruction, so it has the highest priority to be executed. So we know for sure at that time, this must be the time this instruction being executed. Now, instruction 4, can we put into execution next cycle? Then when is the earliest possible time? 5 cycles later than who? 1. Okay, let's put another dependency. Right, so this is the earliest possible time I can execute 4. Now, instruction 5, when is the earliest possible time that I can put it into execution? Next cycle. Instruction 6, who is it depending on? 5. So in theory, I should be able to execute 5 the cycle after, because instruction 5 is an LU instruction. It only needs 1 cycle latency, right? But can I execute 6 right after 5? Why not? because I can only issue one instruction at a time, and 3 and 4 are already here, right? So the earliest possible time of executing 6 is right here, right? Now, how about instruction 7? When? Right after instruction 6. How about instruction 8? Who is it depending on? Do you remember? 5. So when is the earliest possible time I can execute instruction 8? So theoretically, right here. But we have 6 being issued. And then we have 7 being issued, right? So it has to be here. How about instruction 9? Also depending on 5, right? So when is the earliest possible time it could be issued? After 8, right? So if you keep going on, right, it will be crystal clear for you. And you will see, right, after this point, every cycle, I'm issuing an instruction, right? So from this graphical analysis, first of all, don't you feel like that's a lot easier? And the second thing is that it's super easy for you to see what's the CPI. So I can tell you right now, in the comprehensive exam, what I'm going to do is that I'm going to give you a piece of code. You will draw a data dependency graph like this. You are going to tell me what's the CPI. Damn, I heard about that word. All right, but that's the question, right? So here's the thing. The hardware side, we have register renaming and speculative execution to enable more efficient execution by dynamically schedule instruction whenever their data dependency are resolved. However, right now, you might be wondering, whenever I show the demo, I sometimes see the CPI is smaller than 1, right? Why is that, right? And in fact, if you pay attention to the data dependency scheduling that we just drew, at this moment, my memory unit is actually free. Why can't I execute this earlier? Right? That's one issue, right? And the other thing is instruction 12, right? It could be executed a lot earlier, right? Like at this moment, if the instruction 12 is already in a queue, right? So what does that mean is that we are still having a lot of missing opportunities. So to deal with that missing opportunity, here's a new concept called superscalar. So the idea of superscalar is that since we have more functional units now, let's lift that restriction that at each cycle that we can only execute 1 instruction. Instead, I recreate the issue logic to enable the capability of putting multiple instructions that doesn't have data dependencies into execution. So this is the concept of, part of the concept in superscalar is that I am allowing more instruction to be issued at any cycle. And then the second issue that we mentioned is that now, some instruction, if we could have it earlier, then we could have more flexibility in scheduling. So what if we can fetch more than 1 instruction at the same time and put them in a queue and rename them in a queue more at the same time? So the second concept is about increasing the fetch and decode width of your processor. So these two things together is called superscalar. So in this way, you can imagine your ideal CPI would be the minimum of your issue width, fetch width, and decode width, 1 divided by those. So that's the concept of superscalar. So now, I want to fetch more. I want to execute more. So what you have to do is you just make your instruction fetch unit larger and make your issue logic more powerful. Right? So this sounds simple, but it's actually very complicated. So I'm going to skip it. And with that, right, now you can imagine every time I'm fetching and decoding 2 instructions, right? And then I would have more flexibility in scheduling. And if you draw the pipeline like this, you will figure out that at the end, I am always having a lot of instruction being retired at any cycle. So you know for sure this is not a method that I want you to learn. So let's go with the data flow analysis. So with the data flow analysis now, we can have 2 instructions each cycle in the queue. And in the next cycle, because I only have 1 memory unit, so I can still only issue 1 instruction, memory instruction at a time. Now, in the next cycle, because I have the fetch width increased to 2, so I can put 2 more instructions into the queue, right? So for 3 and 4, they are still not ready to be executed, but I know this is the earliest possible time they can be executed, right? So far, we haven't seen any benefit of superscalar yet. But now, the next cycle, I can get 5 and 6 in. At this moment, who can I put into execution next cycle? 5, right? So remember, previously, if I don't have 5 being fetched here, I won't be able to execute 5, right? So you see that's the effectiveness of fetching multiple instructions at the same time. What's the earliest possible time I can put 6 into execution? Right after 5, right? Previously, we cannot do that because we have limited issue width every cycle. But now, because I'm superscalar, as long as I don't violate the rule of my issue width, I can execute them right away, right? And now for instruction 7 and 8, how about 7? Who is it depending on? 6, right? So right here, right? Now, how about instruction 8? Okay, right? So because it's only depending on instruction 5. And the next cycle, the memory unit is also free. So I can execute 8, right? That's something previous pipeline cannot do. But now we are able to do it. Another thing you will find, this is exactly the most aggressive compiler optimization that I would say they can do, right? Now, the processor automatically does that, right? How about instruction 9? After 8, right? Because instruction 9 only depending on 5. How about instruction 10? It's 5 cycle after 9, right? So that data dependency is true, so we still have to wait, right? So if you use the same philosophy, you will figure out this is the resulting execution. And you will find, based on that, if you can execute this for more iterations, then overall, you will find out it will have a CPI equal to 0.62. If you will find like it takes about 12 cycles for every 11 memory instructions, because you will find out the latency is pretty much defined by this chain of memory instructions, right? Your overall latency, right? Like the 7421, they never dominate the execution time, right? However, this part is dominating the execution time, right? Through this analysis, you can find out this is the part dominating the latency. So you can count roughly how many cycles it takes in total, and how many instructions you are going to experience, and to get the CPI. So this is the best way to analyze the performance of a superscalar processor. So the takeaway here is that superscalar further improves the utilization of modern hardware. So why am I teaching you this? If you go through the latest microarchitecture design, you'll figure out the processor pipeline, they don't look alike those ones that you have learned so far. So for example, this is the Elder Lake processor. Don't you feel like this is exactly similar to the pipeline diagram, well, the processor diagram that I showed you, right? And now you understand everything here. Instruction cache. Here's the BPU, branch prediction unit, decode. And in x86, there is a micro op cache. So the thing here is because like after decoding, right, you will see a micro, they use the terminology called micro op because a lot of you might be knowing that x86 instructions, they are hard to pipeline as you learned, right? So turns out x86 internally, they will decode each x86 instruction into a RISC-like micro ops, which is another internal instruction set architecture the processor will use. So when we actually schedule those instructions, what's really being scheduled, being executed are those micro ops. So then when I decode, it's also the stage that I am decomposing each giant x86 instruction into micro ops. And then you will see there is like a renaming stage here. And the allocate means that I'm allocating a reorder buffer for it. And you might see what's the move elimination, what's the zero idiom. So, you know, like right now, x86 processors, they are really highly optimized in a way that I would check the memory dependencies between instructions. If it turns out that I can identify they are moving to the same memory instructions, then I can directly forward a value from one instruction to another without going through the memory. That's one optimization. And the zero idiom is that there are instructions that are depending on lead to zero values. I can zero out those. So I don't really have to really do it, right? So those are the optimization that the processor would do internally. So you can also imagine those are the stuff that is difficult for the compiler to optimize because compiler has no knowledge about the runtime value of instructions, but the processor has it. Right? So it also tells you one thing. Compilers has a lot of limitations. So that's why architecture-wise we have to do that. So after we have done this, there's a scheduler. And as you can see, the scheduler will be able to issue instructions to multiple ports of pipelines. So like in Intel's latest generation, Elder Lake processor, they have 12 ports, meaning that I can issue 12 instructions at the same cycle. And 5 of them are ALU instructions, 7 of them are memory instructions. So in theory, in this pipeline, you are able to achieve a CPI that is 1 divided by 12. And if you only have arithmetic operations, that's 1 divided by 5. If it's memory instruction, 1 divided by 7. If it's branch, 1 divided by 2. Right? Because at the same time, you can issue this many instructions as possible. Right? So based on this, you will know the key to high performance programming is how can I optimize my code writing in a way that I would allow the processor to issue as many instructions as possible in each cycle. Right? And even with the efficient core in Intel Elder Lake architecture, it's still a 5-wide issue pipeline. And this is the same thing for AMD's Ryzen processor, right? They have 4 issue integer pipeline plus 3 issue memory pipeline. So you know the minimum CPI is actually 1/8, right? If you can optimize it further, right? So, but one thing that you will know that those hardware pipelines has nothing like the MIST 5-stage pipeline that you learn in textbook. And all of them are using register renaming, as I show you. So that's why I spend so much time talking about the register renaming mechanism. I want to test you about this because this is indeed how the microprocessors are doing things. So as a summary, we have learned so far that microprocessors, they all have these characteristics. They have multiple issue pipelines called superscalar. They have dynamical out-of-order execution engine that schedule instructions simply based on their data dependencies. They have high performance cache so that we can fetch instruction almost continuously. And also, another key to that is that we have high accuracy branch predictors nowadays. So in the next lecture, which is next Tuesday, I'm going to show you, based on this modern processor characteristics, how are we going to optimize our code as a programmer. All right, so before you leave the classroom today, don't forget that we have assignment 4 due next Thursday, reading quiz due next Tuesday, programming assignment 3 is also released. Enjoy the rest of your day. I will see you next week.